All right, this is the 3-6 video. So if you're watching this, you should be following along, taking notes in your workbook on pages 72 and 73. Our goal today is to use technology to evaluate how well a line fits a set of data. And one new vocab word you'll see today is causation. So if one thing directly causes something else to happen, we would call that causation. Starting with number 1, it says, use the linear regression function to find the equation for the line of best fit for this data here in the table. And in the last unit the last lesson, we talked about drawing our own line of best fit, just kind of eyeballing a line that looks like it's in the center of the cluster of data. Maybe I have a similar number of points above and below the line. But now we're going to use technology to actually get a linear regression, which is precisely the exact correct line of best fit. And to do that, we're going to use Desmos. Here we have the steps in the notes. We're going to go to Desmos.com. We're going to click that plus button to make a table. And we're going to type in this equation, y1, and that little squiggle is on your keyboard. It means like approximately or about equal to mx1 plus b. So you notice that looks very similar to a linear equation. So I wrote that there. Remember, that's y equals mx plus b is slope-intercept form. So really what we're doing is we're looking for m and b, and then we're going to plug them into an equation to get an equation for my line of best fit. So let's go over to Desmos. We're going to take this table. I'm going to copy all those numbers into Desmos. So I go to Desmos.com. You can follow along on your own computer. And I click the plus icon, and I add that exact table from my workbook into Desmos. When I press enter, it'll start a new line for me. And you can see I already typed that equation. And you see that Desmos makes those ones automatically into the fancy little subscripts. So you just have to type y number 1, squiggle, m, x number 1 plus b. And so then it automatically generates this line of best fit perfectly through the center of those points. It also automatically generates all this information about the line of best fit. So we really don't have to do anything by hand. If you forget the equation, this button actually up here next to the number 1 will do all this for you as well. That little 4 points with a line through the middle will do the same thing. But so here we see we have my m and my b. They've calculated it for us. We're just going to take those back to our workbook. And you might notice that the m and b are super long numbers. So when I copy them to my workbook, I am going to round those numbers down before I put them into my equation. So starting with my m, I'm going to stop at the 10th place for both my m and my b. And so to do that, I'm going to look at the next number. It is greater than 5, so I'm going to round up. So instead of 0.7, it's going to be 0.8. Same for my b. I look at the next number. It's also greater than 5, so I'm going to round up to 4.7. And that is my line of best fit in y equals mx plus b form. And so something else that Desmos gave us is that lowercase r. It will calculate that for us, which is my correlation coefficient, one of our vocab words. So question number 2 in your workbook says, what does each correlation coefficient reveal about the data it describes? So if you look in the notes, I wrote a reminder about the correlation coefficient. It is a number between -1 and 1, and the closer it is to 0, the weaker the correlation. If I have a positive number, that means my correlation is positive. If I have a negative number, that means my correlation is negative. So that's the easy part. So looking at A and B are separate questions. They're saying, what does this correlation coefficient tell us? So for A, I have positive 0.1. So that means I have a positive correlation because the number is positive. And so then I look at B. B is negative 0.6. which means it's a negative correlation. And it's as easy as that. So the strong and weak aspect of the correlation coefficient, though, is kind of separate. That's not based on being positive or negative. That's how close is the number to 0. So you see I drew these number lines. You can draw those into your notes too. I think that helps thinking about how close is that number to 0 in terms of from 0 to 1. So r being 0.1, that would be really close to 0, right? These little notches would be like 0.1, 0.2, 0.3. 0.1 is pretty weak, pretty close to 0. So we would say that that is a weak positive correlation. Versus negative 0.6, in terms of from 0 to negative 1, negative 0.6 is almost halfway. I guess we could say it's leaning on the strong side because it's further away from 0. It's closer to negative 1. I could also call it medium since it's in the middle, or sometimes you'll see they call it moderate. And I know you don't have these pictures like I do on the slide. I put those there at the bottom so you could see also a picture of what does a scatter plot look like that's strong versus weak. So if you wanted to sketch a little simplified version of that, the first picture is a weak correlation, right? So my R, you notice, is closer to 0, negative 0.2. That's a weak scatter plot. My points are very separated. They're very far away from the line of best fit. Versus on the right side, I have a strong correlation. They're all super close to the line, close together. Weak and strong. And so what does that look like when I have a word problem, a real life application? Here's an example. So it says the owner of Horizon Flight School created a scatter plot and calculated the line of best fit for her enrollment data. The equation for the line of best fit is y equals 1.44x plus 877. Find the residuals and plot them to determine how well this linear model fits the data. So we can make a linear model for any data. You see they have the line of best fit. I could take any scatter plot and put a line in there that fits it. That doesn't mean that that line actually describes anything about this data. So you might remember residuals is one of our vocab words. It is the space in between points and the line of best fit. So how to calculate it is the y value of the point minus the y value of the line. So to really find the residuals by hand, I would have to calculate the space of all these points. So maybe I'll have like positive 4, negative 3. But in a real world situation, those numbers are only more difficult. So if I really want to calculate all these residuals, I would have to maybe look at my table for the y value of the point and then plug in x to my equation, find the y value on the line. It would take a really long time. So we're actually going to see what this might look like on Desmos. So I'm going to take this table and I'm going to put it back into Desmos. And so I put it here in line 1, I press the plus, and I did our linear regression, and I don't see a graph. So you might notice that my x-axis and y-axis labels are 20, 40, 60, but my numbers are in the 800s. So I could zoom out with my fingers, or I could do the plus and minus zoom on the right side, or I could open that wrench and I can change the x-axis and the y-axis range to match back to the x-axis labels in my workbook and the y-axis labels in my workbook, right? So if I enter that, x-axis goes from 0 to 10, y-axis goes from 800 to 950, I will see my scatter plot here. So that might fix my problem. Now I see my scatter plot. It looks exactly like my workbook. And I want to get the residuals. Well, down here, like I said, it automatically generates all this information. And this button right here under residuals that says plot, we're going to click that. And it's labeled E subscript 1. So then you'll see when you click that, it adds this entire column of all the residuals. So that's what it did. It calculated all the residuals. So it's taking these spaces and then writing them down for each point. So this space right here is in this table. So you'll notice also it plots them, like it said, plot. So it's going to make a graph of these also, but I don't see the graph here. Again, no graph, missing my graph. Notice these numbers, though, are not in the 800s and the 900s. So actually, we're going to go back down to where we were before, back to closer to 0, 0. And so if you zoom out and then zoom in near the origin, you'll see here are my residuals, right? My residuals, look at the numbers, are 40 to negative 22, negative 20. And so if I wanted to plot these like our workbook asked us to, I would do that on Desmos. And then looking at this, I can copy that information into my workbook. So see, I labeled my axes to match what I had in Desmos from 50 to negative 50, and my x values are from 0 to 10, and I copied those points on here. To see what my plot of residuals looks like, what does that tell me? So you'll see I wrote something new in the notes. If it's a good fit, if my line of best fit fits my data well, that means all the residuals will actually be really close to 0 and close to the x-axis. But look at the x-axis here. The residuals are far from the x-axis. None of them are very close. So that tells me that this line of best fit is not a good fit. But really, I could have already told you that. If you see this data, look at it. It doesn't even form any type of linear relationship. My points are not all going up. As the years go up, the number of students is not going up. It's going up and down. It's fluctuating. So really, I shouldn't be trying to fit a line to this. I should be trying to fit some kind of curve to this. So just because I fit my line of best fit in there doesn't mean it's best for the data. And residuals can help me with that. Residuals are a little hard, so if that was super confusing, you're not alone. It's not the most important thing. The most important thing is that we use our line of best fit to make predictions. So that's example number 4, which gives us a equation for line of best fit, y equals 47.83 x plus 2,315.25, and it's supposed to represent a regional air miles in thousands traveled on an airline company. So like American Airlines in X years since 1997. So those were pretty confusing variables, but so they're saying X is the years since 1997. Maybe they opened in 1997. And then they're counting for their business, how many thousands of miles people have traveled. So Y is thousands of miles traveled. And so we're going to try to make a prediction using that equation. If you look in our notes, that's called extrapolating, which I know is a crazy word, but to extrapolate, you guys actually extrapolate already all the time, but that just means we're using some data that we have to make predictions for numbers outside of that data. So say I collect data about I open this airline company, the first few years, this is our data. And so now I want to know though, if we keep growing like this, our company is growing, what's going to happen in year like 20? And I should be able to make a prediction. Like if my company keeps operating like it is, and I fit this line of best fit to my data, it should keep increasing like it was. And I can find where my company will be at even in 20 years if I have an equation for that line. So I'm going to do that. I'm going to use my equation, y equals 47.83 x times x plus 2,315.25. And I'm going to find out what is y when x is 2012. But x is year since 1997. So actually, x is 2012 minus 1997, because we're talking about years since 1997. That's 15 years since 1997. So if x is 15, what is y? So we're going to plug that value x in for x. What do I get if I do that? I get y equals 47.83 times 15 instead of times x. And if I get my calculator out to calculate that, I multiply these two together, I get 717.45. But I still need to add that to this b, my y-intercept. And then for y, I get 3,032.7. I did that in my calculator. And so that means 15 more years from now, we will have 3,032.7 thousands of miles traveled. And so I can use my equation for my line of best fit to make predictions for my business or whatever growth I'm trying to track. And so our last topic is something that we kind of already touched on, correlation and causation. So number 5 is a question about cars and population. In our notes, the most important thing to note is like, what is the difference between causation and correlation? If we're saying two things cause each other, we're saying A causes B to go up or maybe to go down. Versus correlation is just like A and B are both going up. That's the difference. So correlation, I'm noticing this relationship like, oh, A and B seem to both kind of be going up with each other at the same similar rate or something. And then causation is like A is directly causing B to go up. So number 5, you can kind of try on your own, read through this and think about, do you think that this is an example of causation? And write about it in your workbook. And there's another note about causation at the bottom. It is a cause and effect relationship. So after you finish this video, make sure you go back to your workbook and update your checklist and move on to the 3-6 practice, or rewatch the video and ask questions in class. Send me an email with your questions, but you got this.